Hi guys, welcome to today's lecture. Today we continue our discussions on simple linear regression in neural system further extension of simple linear regression. Recall that if we want to study the association between x and y, we'll limit ourselves in this class to the linear association. If the association between two quantitative variables x and y is linear, we can go ahead and use a linear function to model this association. In order to proceed, we first plot the scatter plot in order to check how large is the linear association, and then we compute the correlation. Although there is no specific rule on the cutoff values of correlation, but based on experience, the values of correlation bigger than 0.3 or less than minus 0.3 can be counted as usable correlation, and with that we can go ahead with simple linear regression model. Now if correlation is high enough, depending on the situation, bigger than 0.3 or less than minus 0.3, we can use a linear function in order to model the association between two variables x and y. Recall that a linear function has the following form: y is equal to a plus bx. Of course, we have y and x because these are our two variables, but we need to estimate a and b. We use a method called least squares in order to estimate a and b, and in R we use the lm function in order to find the estimates of a and b and their corresponding p-values. After estimating a and b by running the lm function in R and checking their p-values, we go ahead and write the model. Furthermore, we check the adjusted R-square in order to see how much of variation in y, which is the dependent variable, being explained by x, which is the independent variable. The step-by-step summary of how we should run linear regression model. First of all, we have to specify our variables of interest, and importantly, we have to specify what is our y, our dependent variable, and what is our x, our independent variable. Remember guys, this is very important for us to correctly specify the dependent variable y, independent variable x, because we are either interested in studying the effect of x on y or the amount of variation in y being explained in x. Therefore, it's very important from the beginning that we should know what is x and what is y. Once we have our variables specified, we go for the test of linearity, and for that we plot the scatter plot as well as we compute the correlations. If we were satisfied with the scatter plot and correlation, in other words, if the correlation was, for example, bigger than 0.3 or less than minus 0.3, then we run the lm function in R in order to compute or estimate A and B. Once we have estimated A and B, we check their values, especially the value of B and its p-value. Furthermore, we check the adjusted R-square in order to know how much variation in Y being explained. Once we are done with the values of A and B produced by the lm function, then we go ahead and write the simple linear regression model of x and y and interpret the result. For instance, if you want to study the amount of variation in working experience being explained by the family size, or how much is the impact, or how is the impact of family size on working experience, the first step is to specify the variables of interest. Of course, our variables of interest here are working experience and family size, and importantly, what is our x variable and what's our y variable. Here in this context, our x variable is the family size and the y variable is, or the dependent variable is, working experience. The second step is a test of linearity, and for that I go ahead with the scatter plot and the correlation. Now the scatter plot as well as the correlation, which is 0.93, show a high degree of linear association between two variables. Therefore, I go for LM model in order to estimate A and B and run the LM model of working experience on family size. The summary. In summary, two things are important for us. First, the value of the A, which is 0.86, which is 0.86, and the value of B, which is 0.33, and the p-value of both of them are 0. That means both of them are significant. In addition, adjusted R-square, which is 0.87, that means 87% of variation in working experience being explained by the variation in family size. So, having noted the values of A and B here with their p-values, we go ahead and write the model, the linear model between y and x, in other words, between working experience and family size, and that's nothing but y is equal to 0.86, which is the value of A here, plus 0.34, which is the value of B, x is the family size. That means The impact of family size on working experience is positive. The amount of variation in working experience being explained by the family size is 7%. Often, extreme values or outlying values destroy the linear association. In order to check if we have outlying or extreme values, first we sketch the scatter plot and see the outlying observations. Outlying observations are usually very far from the rest of the observations in the scatter plot. Then we try to remove those extreme or outlying observations and replot the scatter plot and recalculate the correlation. If we see a significant improvement, then we really stick to a new variable with outlying values or extreme values being removed. While removing the outlying values, we should be careful that we should not remove more than 5% of our observations. For instance, if we are interested to study the effect of family size and expenses, first of all, as always, we specify the variables. Of course, our variables are family size and expenses. Importantly, we have to specify what is the x variable and what is the y variable. Of course, here in our case, the x variable is family size because we want to see the effect of family size on expenses, and the y variable is expenses. Second step is to test the linearity. For that, I go ahead with a scatter plot. Scatter plot it doesn't show a very strong linear association between the two variables, and that's being confirmed by the value of the correlation, which is minus 0.008, which is nearly 0. We have two possibilities here. Either the relation is not linear, or the outlying value is actually destroying the linear association. If you check the scatter plot here, we have two outlying values here, far on the right corner, and these are the observations whose expenses is less than 5,000 or 10,000 here. All other observations in our data set are having expenses more than 15,000. Therefore, in order to get rid of these two outlying observations, I redefine the two variables, family size and expenses, and I include all those observations whose expenses are more than 15,000, the two variables, and then double check the scatter plot and the correlation with the newly defined variables which are not containing the outlying values. The scatter plot is showing much higher linear association, and importantly, the correlation is almost 0.43, which is a very high correlation compared to the zero correlation. And that means the reason why the relation was very far from a linear relation between family size and expenses was those two outlying observations. Removing those outlying observations helped us improve the linear association between the two variables, and that gives us the chance to model the linear association between the two variables by taking the function. And for that, I need to compute a and b. And in order to compute a and b, I run the LM function, LM summary, and in the LM function, then the output of the LM function, I have the estimate of a, which is 18.8, which is nearly 19, with 0 p-value, and importantly, I have the coefficient of the family size, which is 0.24, with the p-value of 0. And the adjusted R-square is 0.15, which is a 15% variation, and the expense is being explained by the family size. Okay, now A is 19 with a 0 p-value, B is 0.23 with a p-value of 0.02, which is less than 0.05, significant impact. And I can go ahead and write the model. Expenses equal to 19 plus 0.23 family size. The impact of family size on expenses is positive.